Alright, so Griffiths Electrodynamics, problem 2.20. We start by looking at these two different electric fields here. Griffiths says one of these is an impossible electrostatic field. Which one? Alright, so we'll go ahead and do this part first. So the way we're going to do this is just take the curl of these two fields, because in electrostatics we have the curl of any electrostatic field will be equal to 0. Alright, so one little shortcut is that for a vector equation that equals 0, since if you have an independent basis set like x, y, and z here, then each of these components also has to equal 0, because there's no way they can kind of kill each other because they're independent. So when we take the curl of these things, as soon as we find one of the components that's not 0, then we'll know we've found the imposter, and we'll know which of these fields is impossible. So we'll go ahead and start on a new piece of paper for this. So if we start with A, we're taking the curl of this field here is A. Alright. I'll put a little subscript A on there so we remember which one we're talking about. I'll bring the constant out in front, and we'll just use the determinant. So x hat, y hat, and z hat, d by dx, d by dy, d by dz, and then x component is xy, then we have a 2yz, and we have a 3xz. We're going to take this determinant. And again, as soon as we find one component that doesn't go to 0, then we know this one doesn't work if this is the one. Alright, so so we will start with our x hat part, and for this we have d by dy of 3xz minus, okay, so we did this one, now we'll go minus this one, d by dz of 2yz, okay. Alright, and then we'll have a minus y hat component here. Let's just double check this one real quick to make sure this one goes to 0. So d by dy of this is 0, good so far, but the derivative of this is 2y. So already we have this term that does not go to 0, and we know since the x component of this curl that we're taking does not go to 0, then because the three directions are independent, the curl itself cannot go to 0, and the curl of EA does not equal 0. Okay, and just remember we didn't finish actually taking this curl, so plus y hat of something, well, there's a minus sign in there, whatever, z hat of something, whatever, we didn't have to finish. We know this one is the impossible electrostatic field. Alright, so this one's A is the bad one. Alright, just for fun, why don't we take the curl of B, just to make sure it does go to 0. And we haven't been tricked. d by dx, d by dy, d by dz. Okay, the x hat component is y squared, 2xy plus z squared is the y component, and 2yz is the z component. Okay, comes out front. Alright, so now we have a, in the x hat direction, we get d by dy, taking this one right now, of 2yz minus d by dz of 2xy plus z squared. Okay, and what do we have here real quick? This one gives us a 2z here. Maybe I should write this in a different color just so. Okay, so we have a 2z, and then if we get 0 for this first term here, and we get a 2z, and there's a minus sign, so minus 2z. Alright, so our first term in our curl is 0, so we're off to a good start. Now we'll go on with the second term. So we have a minus y hat, and then we have d by dx of 2yz. So that one's going to be 0, we know that already. And d by dz of y squared. Those are also, that's also going to be 0. So 0 minus 0, and that also checks out. And our final one, z hat. Okay, we have d by dx, this one here, of 2xy plus z squared minus d by dy of y squared. Alright, now we'll get, okay, that term will be 0. We have a 2y in the first part, minus, and then d by dy y squared is also 2y, and so we get 0 again. So this one checks out all three terms, and we know we have a viable electrostatic field in this second equation here, this one here. Right, so this one's bad, this one's good, and now we move on to the next part. Alright, so he says, for the possible one, find the potential using the origin as your reference point. Check your answer by computing the gradient of the potential. You must select a specific path to integrate along. It doesn't matter what path you choose, since the answer is path independent, but you simply cannot integrate unless you have a definite path in mind. Alright. So now that we found our good field, go ahead and copy that onto the top of this page, so we have it with us. Y squared x hat plus 2xy plus z squared y hat, here's our winner, plus 2yz z hat. Barely have enough room. Okay. Alright. So what are we here? Okay, we are going to find the potential using the origin as our reference point. Alright. So the potential is equal to minus the integral from some origin to some, the point that we're interested in, of e dot dl. Okay. Now, if we look in our front of our book, we see that this dl in Cartesian units is dx x hat plus dy y hat plus dz z hat. Okay, so let's go ahead and take this dot product real quick. Okay, so we'll have the k out in front as always. we have a y squared dx plus we have this 2xy plus z squared times dy. Jump down to this next line here. Plus we have a 2yz dz. Okay. Alright, so now we just have to integrate this along some path. And we'll run into trouble if we don't use a path like Griffiths tells us to. So we will go out to some point r, and let's just call r x prime, say. This is kind of confusing because, well, I don't know what's more confusing. Using primes like Griffiths uses for source points, or not using them and using the same. We'll just try and be careful here, and wow, I cannot talk and write at the same time. Okay, all right. So z hat, y hat, x hat, right? Okay. Now, so we're going to go ahead and take a path, and why not just go in order? We'll start just along the path of x, where y and z equal 0. So if you have a coordinate system, and this is x, y, and z, and you have a point out here somewhere in space, we're just going to first follow the x-axis, and then why not? I'm going to draw this a little bit differently so we have some perspective here. Alright, so we'll say we follow the x-axis first, then we'll follow the y-axis, and then we'll follow the z-axis over. I hope this makes sense. I tried to draw all the lines parallel, but alright, so this point is just out here in space. Alright. So for our first, and so we'll do these into 3 different integrations, and we'll add them together to get along our entire path. So first we have a y equals 0 and z equals 0, and we'll also have dy equals 0 and dz equals 0. We're not following those directions at all. Only moving along x. Here's where it gets a little confusing. I'm just going to write these just to remind us which one is the variable that we're following. Maybe it works better in, I don't know, a computer program or something. But all right. So our first integral. Let's see. Go back and find what our integral even was. Okay, I think this is it, right? Okay, so it's this thing. Alright. So for our first path, when we write this out, we have, okay, so if we have, I'll just write out first, okay, v equals minus integral from the origin to point r of e of zl. Okay. equals minus from 0 to the point x, y, z. Again, Griffiths kind of suppresses the primes on the dummy indices when he does his integrations to not get confused with the source point, and that's kind of what we're doing here. Okay, and then this e.dl we found, which is kind of long, probably goes into two lines here. We have this k y squared dx plus, it's getting kind of messy, 2xy plus z squared dy plus 2yz dz. Try and write a little bit bigger because these are kind of meshing together. Alright. Okay, this is kind of a mess, but hopefully it makes sense as we go along. So so our first integral, which I'll just call v1. Okay, we're going to follow this path up here. So we set y equal to 0, z equal to 0. So in our first part, this term is going to go to 0 because y is equal to 0. And in these ones, we already know because dy is equal to 0 and dz is equal to 0, those two both go away. So all three terms are going to go to 0. So I'll bring the k out front, and I'll just write this one down because dx is not equal to 0 here. Right? We were going to go from 0 to the point x. All right, but again, y is equal to 0, and this just gives us 0. Okay, so that's our first leg of our journey, turning into quite a long problem. Our second leg, now we are going to go along y, right? So if I can write this, we have y equals y, right? Dy equals dy. But this time, so z equals 0 still, dz equals 0 still. But we're at x equals x, but dx is equal to 0, right? We're not moving in the x direction at all, but we are we're out displaced from the origin along this line here this time. So we're at x equals x. Again, kind of confusing. Maybe the computer programmers, maybe it looks more natural to them. All right, so we're going to go ahead and do this integral 0 to y this time. And what terms do we have? Well, dx is going to go to 0, and dz is going to go to 0. We're just looking at this one. So we have 2xy plus z squared dy. All right. But z, we know, is 0. Okay, so now we just have this little piece right here. All right, so the second leg of our journey, minus k, and here we have x y squared. Right, so we just raised y to 2 divided by 2, that kicks out this 2, and we have an x y squared. And when we evaluate that from 0 to y stays there, minus 0, and we just stay here with x y squared. Right? It may look kind of abbreviated or abridged, but that's what we get. All right, now we'll move on to our third path. So now we have x equals x, dx equals 0, because we're not moving along x, we're not moving along y, we're moving along z this time. But we're out in this plane of x equals x, but we're also in the plane here where y equals y as well, right? So x equals x, y equals y, dy equals 0, z equals z. Now this is the one that we're changing, and dz equals dz. All right, so we toss out the first two terms because they have a dx and a dy in them. Now we're only focused on this term here. And we write out our integral along this path. We're going from 0 to z in the z direction. And so we have 2yz is our integrand. Okay. All right. And again, y doesn't equal 0 anymore. Y equals y. All right. So now, what do we get here? Well, we're just going to raise z to 2, divide by 2, so we get yz squared. And just like before, we're just integrating from 0 to z. So here we go. Minus k, and then we have a yz squared, just similar to what we did up here. Don't even need the parentheses, but why not? All right, so when we add up our v equals v1 plus v2 plus v3, well, v1 was 0, v2 is this, and v3 is this. So we can factor out a minus k, and we get an xy squared plus yz squared. Okay, so this is our potential. Put this in a little blue box, it's easy to find. And, all right, so now, let's see. All we have to do is compute the gradient of v and show that we get the original field back. All right. So E is equal to minus the gradient of v, and so equals minus the gradient of k. Put this in a bracket so it's clearer. Xy squared plus yz squared. Again, kind of sloppy with notation and everything, but that's how it goes. All right. So, oh, and I forgot the minus sign in here. All right. So this minus sign, we'll get rid of that minus sign. We can bring k out in front since it's a constant. And then we just have this. All right. Okay, so let's do it. K comes out in front. All right, we take the derivative with respect to x, which is just y squared in the x hat direction. Now we take the derivative with respect to y, so we get a 2xy plus z squared in the y hat direction. Now we take the derivative with respect to z, so we just get a 2yz in the z hat direction. Now we compare this with our original field, which I wrote right here. So here's our k. We have a y squared in the x hat, 2xy plus z squared in the y hat, and a 2yz in the z hat. So we just checked that our electrostatic field turned out all right. So, long problem, lots of sheets of paper, and a lot of sloppy math, but I think it worked out all right.